Biodegradable polymers are polymers which break down naturally after an intended amount of time. They have applications in plastics and packaging, controlled drug delivery in pharmaceuticals, and material science or engineering. Their natural degradation makes them promising replacements for some non-environmentally friendly petrochemical products. One very interesting biodegradable polymer is polylactic acid, or PLA. PLA is the result of the polymerization of lactide, which comes from the fermentation of starch or cellulose. This is a major advantage PLA has over certain petroleum-based products. That is, it can be mass-produced from renewable sources such as corn and sugarcane. Alternatively, PLA can be made from glycerol. This approach is also environmentally friendly because glycerol is one of the products of biodiesel production. PLA is used in industry today for domestic products, engineering materials, and medical devices. Some of these include water bottles, hats, shirts, plastic cups and utensils, food packaging, electronic casing, coated cables, scaffolding for tissue growth, and drug delivery devices. In general, there are two ways to make PLA from lactide. The first method is a condensation reaction, but this is typically undesirable because water produced during the reaction causes chain transfer, resulting in low molecular weight material. Furthermore, the condensation reaction must be done at approximately 200 degrees Celsius to work. For this reason, the method of ring opening polymerization is the preferred method for PLA production.
The production of PLA through the use of glycerol feedstock can be broken up into three general steps. The entire process flow diagram is shown here. The first step of the process flow diagram contains reactions that yield lactic acid. During the second step of the process, the lactic acid is converted into racemic lactide. The third and final step of the process contains the polymerization of the racemic lactide into stereoblock polylactic acid. Each of these steps contains various components and inputs that are detailed in the following slides.
In step 1, glycerol and sodium hydroxide are inputted to the first reactor. This hydrothermal reaction yields a vapor stream of hydrogen gas, which is released, and sodium lactate, which is the salt of lactic acid. The sodium lactate is then passed to the second reactor, where sulfuric acid is added to the system. This neutralization reaction yields sodium sulfate and lactic acid. In order to be able to separate the lactic acid and sodium sulfate, ethyl acetate is added and all three substances react in reactor 3. This effectively separates sodium sulfate along with water, but leaves lactic acid and ethyl acetate in the product stream. These two can be further separated in a distillation column. In this case, lactic acid exits the distillation column as a liquid, and ethyl acetate is boiled off and released as a vapor.
Due to the fact that the reaction yielding lactic acid in step 1 consists of two acid-base reactions, the yields are very high, and as a result, no recycle is necessary. Simply put, the yields of acid-base reactions are typically very high due to the highly favorable thermodynamics they exhibit.
In step 2, the liquid lactic acid is transformed into meso and racemic lactic acid. This conversion is obtained through the use of a catalyst. In this case, antimony trioxide is used. Due to a poor first-pass conversion, lactic acid is still present in the product stream. Thus, a distillation column must be used. In order to reduce waste and to increase the overall conversion rate, the lactic acid is recycled back to reactor 4.
Reactor 4 introduces an equilibrium of lactic acid and the oligomer. This oligomer is a necessary intermediate in lactide formation. The oligomer must undergo a ring-closing elimination to form the product lactide. For the lactide to form, the oligomer must be around its 10 to 20th degree. As a result, a high single-pass conversion is never possible. To resolve this, a recycle takes the lactic acid and the oligomer back to the reactor after lactide formation. Note that the mesolactide is far more volatile than D or L-lactide. As a result, the mesolactide is removed here.
In the third step, the lactide produced in step 2 is transferred to the fifth reactor. Here, a catalyst must be added to assist in the polymerization step. In this case, stannous octate in methanol is chosen as a catalyst because it assists in the polymerization of high molecular weight polylactic acid. After precipitation, the methanol and unreacted lactide is recycled to reactor 5 and passed through the system again.
With the aid of stannous octate catalyst, lactide can undergo a ring-opening polymerization yielding PLA. The stannous octate is a metal catalyst with sterically hindering ligands. These ligands protect the PLA intermediate while it is associated with the metal catalyst, allowing for a very orderly formation of PLA via a highly elaborate mechanism. The stereochemistry of PLA depends on the monomers from which it is formed, because during the ring opening polymerization, the stereochemistry of the chirocarbons were conserved. In the process, only D-lactide and L-lactide are used to produce PLA. In D-lactide, both chirocarbons are D. In L-lactide, both chirocarbons are L. The importance of the stereochemistry lies in the different physical properties they produce in PLA.
The L isomer has a higher melting point in density than its D counterpart. The higher melting point of PLLA broadens its use in applications, as it will maintain its structure in hotter conditions than PDLA will. Also, its glass transition temperature is greater, which is significant when analyzing polymer chain mobility behavior.
The physical properties of PLA can be manipulated by changing the isomerization or molecular weight. This appealing characteristic permits some freedom on the properties to be fine-tuned to a specific or general application. Referring to Table 2, the PLLA that is more rich in the L enantiomer exhibits higher yield, tensile, and flexural strength than the PDLLA. Given further development, one could imagine how specific enantiomeric isomerism could yield specific material properties optimized for specific applications. Since the alteration of stereochemistry allows for the adjusted physical properties, it is important to understand the isomerism of PLA.
The rate at which a PLA sample degrades is most dependent on polymer reactivity with water catalysts. PLA hydrolytically degrades in two general steps. First, the molecular weight is reduced by the scission of ester groups within the molecules. This separation occurs randomly and non-enzymatically, which are conditions reflective of those in nature where the polymer material may be discarded after consumer use. Secondly, the molecular weights of the compound blocks continue to decrease as microorganisms metabolize lactic acid and low molecular weight oligomers to carbon dioxide and water. Any factor of reactivity, such as particle size and shape, temperature, and isomer percent, will take some responsibility of the sample's degradation rate. The overall degradation process lasts several months in a wet environment. This figure illustrates the degradation and production cycle of PLA. The carbon dioxide and water products of the degradation of PLA return to the earth and aid in the growth of plants for plant oils, starting the PLA process again. Because of its adaptability, PLA finds uses in many applications, including packaging and medicine. Shown here are some uses of PLA in the consumer and medical world. It is quite possible that some of the food you eat came to you in a PLA container. The medical devices shown here are bone fixation screws and surgical meshes. While PLLA can be processed by the human body, PDLA cannot because the body lacks the proper required enzyme. Therefore, when studying the food packaging applications of PLA, it is important to include as little as the D isomer as possible to avoid its negative effect on humans. PLA manufacturing costs between $2 to $4 per kilogram, where the traditional alternative, polyethylene, has manufacturing costs of about $1.50 per kilogram. Until PLA production is engineered to cost less, it cannot fully compete with its fossil fuel-based alternatives. Nevertheless, PLA is a useful packing material in the consumer world. This slide depicts some of the many medical applications of polylactic acid. Drug scaffolds are structures made of PLA that will support different cell types during gene therapy. In drug delivery systems, PLA will protect the drug in microcapsules and microspheres for controlled release. In surgical sutures and meshes, PLA can be used to stitch lesions or as a mesh for body wall repair. This kind of research is actually being done at the University of Pittsburgh right now. In implants and bone fixation materials, biodegradable materials eliminate the need for an invasive removal procedure later.
In conclusion, PLA is a versatile polymer with innovative applications in packaging and medicine. Due to its adaptable physical properties and hydrolytic biodegradability, PLA offers a sustainable solution to meet increasing consumer demands in an environmentally conscious world. As ring opening PLA production methods become more precise and the demand increases, the cost of production should fall, making it as economically viable as current petrochemical-based plastics. Ideally, environmentally friendly polymers such as PLA will replace their petroleum-based counterparts in the future.